Hey, welcome to week two. We're gonna dive right back in. Just want to take a little bit of time to make sure there aren't any questions or concerns before we get started. As you think about that, I will be getting up the next assignments for the first assignment over the next couple of days. Should we do a week from Wednesday, just to make sure that people have enough time to iterate on it. I tend to make slightly larger assignments than you might be used to and/or assignments that take a while. So when I do post it, please make sure that you take a look at it and get started early so that you can get stuck early and ask questions before it is suddenly the day that it is due and not very much of it is done and you need assistance. All right, last time we were finishing up our review of computational complexity. I don't anticipate that it's huge review for some of you, depending on where you took data structures, how you interface with it. But we're on the road to the first major unit of this class, and we will get there in just a few slides. I want to take a little bit of time, though, to apply a bit of what we've learned to an actual algorithm. So we've done this a little bit with some of the algorithms that you have mentioned in class, but I'm going to take insertion sort, and we're going to just apply these ideas very briefly in ways that we already have in class, but again, just cementing the idea through the use of analyzing a real sort algorithm. A lot of this we've actually talked about in class already, but of course it takes a lot longer to sort 1,000 numbers than 10 numbers. So this is why we care about the order or the complexity of that. We've also talked about the underlying data representation. So sorting 10 numbers that are already in sorted order, sometimes faster than sorting 10 numbers that are sorted in reverse order. Depends, of course, on the actual underlying algorithm, but for insertion sort, we are going to be walking back each number until it is in place. So if something is already in place, then there is no walking back to do. And if something is reverse sorted, then that is the worst underlying representation. We have to walk every number we see all the way back because it is the smallest number that we've seen so far. What if we used selection sort instead of insertion sort? So I guess first, what is the difference? How does selection sort work?
Like swap two values using like a
Yeah, we're going to look through every single value in the list. We're going to identify the position of the smallest number, and we're going to swap what is in position 0 with where the smallest number is.
Yeah.
So that we know after the first iteration, the smallest number is in the index 0 or the first position. We then loop again over the remainder of the array, everything that is after the first position, find the smallest number in that, and we'll swap that with position 1. And continuing to do that until there's nothing left. So that said, which takes longer, sorting 10 numbers already in sorted order or sorting 10 numbers in reverse order?
I think, well, it would still take longer, right? But it just so happens if it's in reverse order, you're replacing, when you find the smallest value, you're replacing it with a larger value. So by the time you get halfway through it, they're sorted. Right?
So you'd be swapping, if we have 10 through 1, you'd be swapping 1 and 10 is in place, but how would we know that 10 is in place? By the time we reach that, we still have to go search through everything to make sure, because we didn't know that they were sorted in reverse order, and we're not keeping track of the fact that they were sorted in reverse order as we did it. So yeah, by the time we get halfway done, we would be done, but we still have to validate that we are done. And that process still takes the same amount of time as if they weren't in sorted order by how this algorithm works. Yeah.
I think if you sort that finds that the number is already in the place where it needs to be, then we get that. So I think faster.
How would you know? So let's say the first element is the smallest number. You still have to look through every element of the array to know that that is the smallest number and its
And then you-
location is there.
But then you skip the swapping step.
Right.
So you get to skip one step, so it's.
Yeah. Yeah, you would have something like an n squared minus n.
Yeah.
Yeah. It would be ever so slightly faster, but not asymptotically faster. That's a good point. So depending on the algorithm, it might not matter what order the underlying data is in, whether it's in its best case or its worst case. Insertion sort has a faster best case than its worst case, and selection sort barely has any difference whatsoever between its best case and its worst case. So it's worth considering whenever we are looking at algorithms like this. Does the underlying order matter? How so? How is it efficient? How is it not? We can't generalize one sort to all sorts. Just because insertion sort behaves in this way does not mean that every sorting procedure behaves in this way. We have to analyze it algorithm by algorithm, process by process. So we want to analyze the algorithm itself rather than how it behaves on a particular computer, on a particular input. Why does it matter that we look at the algorithm rather than the particular computer? I think I've asked this before. But computers are different. And so an algorithm may be faster, a slower algorithm may be faster on another machine than the slower algorithm, I guess, than the faster algorithm written on the, coded on the slower machine. You code the slower algorithm on a faster machine, the faster algorithm on a slower machine, then we can't easily compare the running times of those two algorithms based solely on how long it took to execute on the computer. It doesn't reveal any information about the algorithm itself. It reveals information about the computer you're running it on. And that doesn't determine whether a client using different machines should use one algorithm or another. That ends up confusing that whole process. So we try to keep the machine the same, and even better, remove the machine from the analysis completely, because we don't want to make any takeaways, take away anything from that process, or from using a particular computer. So let's try something else. I will reveal here some pseudocode. We are going to start to look at this weird function that we're going to start thinking of in terms of, we're going to start using this T of n to represent something recursive. But insertion sort doesn't have to be recursive. We can still think of it iteratively. But let's devise a mathematical function, taking the size of the input, outputting the number of operations needed to solve the problem. Here is a full insertion sort. Now we're not just looking at some arbitrary piece of code. We're looking at a real sorting algorithm. So let's actually go see if we can derive the running time that we actually know for insertion sort through looking at this line by line. So take a minute or two, look at the code and see if you can figure out how many times this is run. Again, based on the input size. Right. What are we finding? This map to how we understand insertion sort? Feel like you're looking at insertion sort? Hopefully.
It does, to an extent.
The main reason I put this example in here is this is how our book that we'll use for this quarter disseminates this information, as opposed to a lot of the data structures material and the data structures book. Is how I got most of our past examples. Our algorithms book is a lot more technical and mathematical and a lot less intuitive. It does explain things intuitively, but it will default to a mathematical representation. And so as we see exactly how they are going to analyze the running time of this function, we can actually look at how this relates to what we've seen before. Let's make sense of this. Take a second, and once you feel confident, somebody let me know how they are interpreting the running times that are on the far right column here.
Oh,
What do we see? What's with this summation notation? The n and the n minus 1 are the number of times that these lines are being run within
Yeah.
a single for loop. But what do we know about how many times the lines inside of this inner while loop are running?
well, the goal for, yeah, the goal for as long as j is greater than 0 and, the array, wherever j is indexed, that is great, and the key, and it breaks whenever, either of those things. Trying to think of the words here. Once either of those conditions are not fulfilled or broken.
Yeah, it differs between the best case and worst case performance.
Yes, it does. So I'm trying to think, summation notation involves something closer to. I don't know, it's familiar, too familiar, reminds me of factorial actually, from what I remember doing last quarter.
Should not make you think of factorial.
Not entirely, but it's, no, that's not it. I'm thinking of like that, basically it's being, every value comes in and then it's all added together in that summation notation. Every result of ti.
Yeah, the question is how many times are we doing this? And it's variable depending on how many places back we need to move this number before it is in place. Its best case, it's already in place because it's the largest number we've seen so far. Worst case is so far, so it has to move all the way back to the beginning of the sort of the portion of the array. So mathematically, how you can analyze this, and this is going to look a little bit grosser.
It is grosser, but I see your point.
Is we have these names now for these costs, C1, C2, all the way to C8. So we can throw them together in terms of how many times are each of these lines being run. And as we do this, we end up with a function based on the average number of places back, or how many times that these numbers are being moved back. And we can take an average, if we're interested in average case, we can assume the worst case, and T sub I can be replaced with any of those. The worst case meaning we're moving every number all the way back. The best case, we're not moving it at all. The average case, some calculation of an average number of steps. But we have now a placeholder variable for that concept of how many operations do we need in order to get the next number in place. Because we don't know that. It's going to depend on the underlying data representation. So we need some way of disseminating that it depends on the underlying data representation. And here is one way we can do that. Yeah,
So T sub I represents the conditional in the while loop?
it's the number of times that we are going to be moving something back. So if we look at, I should zoom out just enough to see the code and this. So we see that the while loop itself is being run
See some of the.
n minus 1 times, which is based on this summation of I equals 2 to n that will run n minus 1 times. But that loop itself will be running, how many times are we running that statement? That will depend on the number of places back, because we go back to that inner loop and check that condition each time until it is in place. If it happens to be in place immediately, because that number is the largest number we've seen so far, that runs once. But if it is the smallest number and it has to move all the way back through the array, then we're going to run that while condition as many times as it takes to move it back to the beginning of the sorted list. Does that make sense to people?
I think so.
I get a decent few blank stares. So we're running this code. I can draw right on the code here. So we know everything that's happening here. This is all determined for us, basically. There's no question about how many times anything in the first half of this is going to run. But as soon as we reach this while, the question is, if we have a sorted portion of this array, I'll call it an array because it doesn't matter. Let's say we have 3, 7, 9, and 17. I'm feeling very, for the most part, prime except for 9. And we're trying to, there's this part is the sorted part of the array, and we're adding the next number on top of this. If this number is 20 something, 26, then the number of times we need to check this is just the once. One time we check, we see that j is greater than 0 and a of j is greater than b. That's false. It's already in place, so we can just loop ahead and check the next position. So this gets run once. But if this number is 2, on the other hand, we're going to need to check that while condition as we store off the 2. We're going to move the 17, we're going to move the 9, we're going to move the 7, we're going to move the 3, and then put the 2 in place. And each time we move a number, we're going to be checking, when we run this that moves it into the next position, we're checking the while condition again, and again, and again, and again. So the upper bound for this is going to be the length of the sorted part of the array plus the number that we are sorting now. So that's what this T sub I represents. It's the number of times that we have to check this in order to move it back into place. And the best case of that is this is the largest number we've seen so far. Happens once. Worst case, we have to move it all the way back to the start of the sorted portion of the array, and that's going to take as many times through this inner loop as we have elements in our sorted list. And anything in between is somewhere in between that. So that's the upper bound and the lower bound. On average, you would expect to move it about half that far as an expectation, about half of this total distance. You would expect, just because if things are averagely sorted, you would expect them to move. There's a chance, an equal chance to move it in any position in the array. So on average, you'd move it about half the distance. But it allows us to factor this out as a variable. Because when we disseminate information about the algorithm, we don't want to make any assumption about the underlying data representation. If we disseminate it as a variable like this, when someone is looking at this algorithm and they want to determine its best case behavior, how does it run when the underlying data is already sorted? Then the algorithm isn't telling us, this dissemination isn't telling us anything. It's in a variable form that we can instantiate and see its behavior. So this book will do this a lot. It will not make any assumptions, and it will give you the mathematical nature strict of those assumptions. Yeah.
Trying to figure out how it wanted to use this equation. Had a data set that is how.
Yeah.
How would you? What would you write to somebody if you think sorted or would you write?
Yeah, the entire purpose of this is to determine what the associated order is. But because we know the best case and the worst case behavior of insertion sort are different, then that means the conclusion is different if we make a best case assumption or a worst case assumption. In our best case assumption, you're replacing T sub I with 1, basically. And now you have the ability to determine the number of times this C sub 1 is run. You're replacing C sub 1, whatever the cost of this is. So how long does it take to run this line once? That's that cost times n, the number of times we're going to run it.
Okay.
And then we have C sub 2 times n minus 1. So it's going to say n minus 1 times however long it takes to do this. That's how long we can anticipate that running. This would be more of a millisecond by millisecond analysis. If you could determine on a particular machine, here's how long it takes to run this. But for the most part, we're going to be replacing this C sub 1 and C sub 2 with something like O of 1. So it's n times some constant behavior, which is in order n. Yeah, but it allows us to replace this with either 1 or with n over 2. If we're doing best case is 1, worst case is n, average case is n over 2. Something like that. Does that make sense to people? Kind of an all-encompassing formula that you can take your own assumptions, plug in, and get a result from that is informative. It's not doing all of the work for you, it's abstracting at the level of where might your assumptions be, best case, worst case, average case behavior. Here is how you would plug that in to get the associated result. Questions before we move on to the next slide? Okay. So we already know how insertion sort works. Fastest process is an already sorted list, so we can immediately plug in for that. And we get, after some simplifying, C1 plus C2 plus C4 plus C5 plus C8 times n minus C2 plus C4 plus C5 plus C8. And we can see how the assumption of best case leads to something that looks linear. Each one of these costs from before is a constant time operation in actual code. So we have some constant times n minus some constant. And this should asymptotically lead us to a linear time conclusion. If we make an assumption that the list is reverse sorted, we can plug in the assumptions for what happens, how many times we need to work with that T sub I. And we end up with something a little bit more complicated. Look at the simplest form down here to give you a sense of, we have C5 over 2 plus C6 over 2 plus C7 over 2 times n squared plus C1 plus C2 plus C4 plus C5 over 2 minus C6 over 2 minus C7 over 2 plus C8 times n minus C2 times plus C4 plus C5 plus C8. So we have some constant times n squared plus some constant times n minus some constant. And this should, once we analyze this asymptotically, lead us to a quadratic assumption. So this is a much more rigorous form of analyzing how and why an algorithm leads to a particular asymptotic runtime. And this all just comes from the equation on the past slide. And just plugging in the assumption of if the list is reverse sorted, how many times are we running each one of these lines with this associated cost? That's all the C's are, is the cost of running a particular line in the code. In general, this is slight overkill. Oftentimes we can intuitively see the result, but sometimes the intuitive results can lead us astray. So sometimes we need to backtrack down into this level of analysis just to be absolutely sure that our assumptions are valid. Occasionally, you will find someone who does not believe you. And if someone is arguing with you over something that is apparent to you, sometimes you need to break it down into the actual components that build up your argument. It's hard to argue with something that has been broken down to this level. Yeah.
Really important, shouldn't the C's be?
C's be equal.
Yeah, shouldn't C1 and C2 and C3 be the same amount?
It depends. So the book / this algorithm is not assuming that they are constant time. They are all a constant time operation. But if you analyze one of these and realize that it's an OS call plus underneath the hood, one might take 10 times longer. So there might be a 10 times longer constant associated with something. When we're worried about asymptotic runtimes, none of that matters. But if you're looking at the constraints of a real world system, you would probably want to break it down into those constant time operations just so that you can see where should I be prioritizing my efforts on making this run faster at a constant rate. You're not increasing the asymptotic runtime, but you want to make this process faster. If one C is 10 times the size of another C, it's just a constant factor, then it's 10 times is worth your attention to try to make that faster. Because it is a bigger bottleneck to the runtime of the system as a whole. But yeah, in terms of asymptotic runtime, they're all constant. That is a good question. Okay, so we can take this idea and directly correlate it to a best case and a worst case running time. We can see the linear nature of the best case. We can see the quadratic nature of the worst case. And the average case is somewhere in between with a good bit more work. Average case is usually the hardest one to find. So yes, this certainly seems tedious. It's something that you should do in the worst case when you need to. But we can see that the expressions contribute differently to the scaling of the running time. And this is why we take the order of the running time rather than relating quite as detailed a formula for exactly how something like this runs. So unless you are responsible for an entire system like this, analyze it from its asymptotic runtime. We've already talked about most of this. Then we also talked about why we most frequently relate the worst case behavior as opposed to all three: worst case, best case, and average case. Just because worst case gives you that upper bound, worst case is usually the easiest to calculate, and the average case is usually closer to the worst case than the best case. So we can do the most, we can say the most with the least work by just analyzing the worst case behavior. So average case is difficult, typically closer to the worst case than the best case. We wanted to figure out the average case for insertion sort. What would we have to do? How would we go do that? We would need to know how far a data point moves on average when we go through that innermost loop. And it is about half if the data is randomly distributed. So you take the worst case behavior and you cut it in about half. But since cutting something in half is constant, the order of the average case is the same as the order of the worst case. You divide anything by 2, it's just a constant. So the average case for insertion sort is not too difficult to figure out, but again, you're making assumptions when you do that. So as you do some worst case analysis, another reason why worst case is important is it creates that upper bound, that deadline. If you have some kind of constraint, this algorithm needs to finish within this amount of time. The worst case behavior will tell you whether that is guaranteed or not. So in real time, when you have those constraints, worst case becomes the default. And we will see the worst case occurs fairly frequently for a lot of algorithms. If you are searching a database for a piece of information, searching algorithms worst case occurs because data is not present in the database. So you have to search through the entire thing in order to know that it's not there. In tree-related structures, how much of the data is on the lowest level? If you have some kind of binary tree, where we have a root, we have, imagine that this process continues and that it is a full and balanced tree. Of all of the data in this tree, how much of it is on the lowest level? Half of it. There are n-1, n/2 - 1 nodes in every level except the last level. And then basically n/2 nodes in the last level. And this would be the case as we go level by level, just because each level has twice as many nodes as the prior level. And you can think of this in terms of a binary number. If we're storing 1 piece of data here, 2 pieces of data here, 4 pieces of data here, then you have the 1's place, the 2's place, and the 4's place of a binary number. So if you have 3 digits to store your binary, how much of those 3-digit numbers starts with a 1, saying that it's on the lowest level? It's half of it. It's relatively equivalent to just analyzing binary numbers or any other binary work that you might do. So a lot of times in how we structure computer science, worst case is a fairly accurate measure. Last piece of summary, we talked about worst case, which is our big O notation, gives us a mathematical asymptotic upper bound. We know for sure the algorithm runs in less than or equal to this asymptotic order. So if we say something like it is big O of n squared, there may be inputs for which this runs at a faster order. There may be some inputs that run in n, insertion sort, as a worst case quadratic asymptotic algorithm. But if it's already in sorted order, it runs in n. We would still call this big O of n squared because in the worst case, it's going to take us a quadratic amount of time. But there are inputs for which this takes less time. We use omega notation to give us a mathematical lower bound, an asymptotic lower bound. This says in the best case, the algorithm runs at this order, but there may be inputs for which the algorithm runs at a higher order. So if we were to say this for insertion sort, what is the big omega notation for insertion sort? It runs an omega of what?
N.
Omega of n, yeah. The absolute best case for this is that it's already in sorted order, but there may be underlying data representations for which it runs worse. It just happens for insertion sort. It's just about everything that isn't immediately completely sorted. So disseminating best case runtimes. Theta notation gives you an asymptotically tight bound. It says the best case and the worst case lie in this particular order. So don't use theta notation unless the best case and the worst case have the same asymptotic bound. So the algorithm runs in exactly this order, always, regardless of the underlying data representation. So selection sort runs in theta of n squared. Doesn't matter if the data is in sorted order, in reverse sorted order, in randomly sorted order. It will take an amount of time to run proportional to the size of the input squared. So we get an asymptotically tight bound. So make sure that you're using the appropriate symbol to disseminate what you mean. And no matter which one of these you use, lower order terms are ignored, constants are ignored. It's still an asymptotic word. It's just a matter of, are you looking at the worst case behavior, the best case behavior, or an asymptotically tight? The best and worst case is the same order. Therefore, it always runs proportional to this scaling factor. Questions about any of this before we move on to the next set of slides? This is the end of slide deck 1. Show of thumbs, how do we feel about asymptotic notation?
Better, at least. I think I understand enough for now, just need to practice something.
I see a lot of practice would be good. A lot of practice would be good, and I see a good few people who are confident in this as well, which is good. I don't see many or any completely down, so that's good. If you would like some additional practice with this before we get started with homework or just to talk through your experience, feel free to come talk to me during office hours. I'd love to have that conversation. Okay. We're going to dive into divide and conquer, which is the algorithmic way of stating recursion or recurrence relations. That's a way we're going to analyze how a recursive function behaves asymptotically. So we've looked at iterative methods, we've looked at code, but we haven't looked at code where the running time isn't necessarily inherent in the code itself. The question is, how many times is this method called as we work from the input case down all the way to the base case? So we'll start there. So the class of algorithms that are recursively defined, those of you who have studied merge sort, think merge sort. What else have we looked at historically that is recursive? What have we implemented? What have we done? Yeah?
Factorials.
Yeah. Anything you can do iteratively, you can do recursively. The question is just, should you? Yeah, why do we study recursion? If everything that can be done iteratively can be done recursively, why do we care about recursion? Yeah. It can be significantly easier to implement one way or the other. The way that I like to show this is with implementations of the Tower of Hanoi. The reason we study that or use it as an example is the recursive version is in Java, something like 7, 8 lines. And the iterative version is 20, 30, 40 lines to implement. Does anyone have a sense of why that might be? Why is the recursive version so much shorter and simpler than the iterative version? Yeah.
Because you're, I jumped off it, because you're, you're reusing the same codes.
Yeah, you're reusing it, but if you're doing this iteratively, you have to define your own stack. And we use this concept of a stack in the form of the call stack if we are doing this in terms of recursion. We're using the fact that the way this happens in practice is when you call a recursive method, you're using the call stack. An instance of this method is being called on top of the existing method, which works just like a stack. The information that you would need from a stack to solve Hanoi is already inherent. That structure is already inherent in the call stack. So you don't need to specify any of that logic. It's already built in to how functions call other functions. And that saves you a lot of time and lines of code in practice. I wish I had that prepped and ready. I kind of, sort of, I might take a couple minutes at the end of class. If anyone wants to see the kind of recursive implementation versus an iterative implementation of Hanoi. But we have for recursion, 3 distinct steps. We need the divide step. We're going to take the problem that we currently have. We're going to divide them into some number of subproblems that are similar instances of the exact same problem. So if we're looking at merge sort, we have a large unsorted array. We're going to divide this into 2 smaller unsorted arrays. So you get 2 versions, 2 instances of the same problem, but the size of those problems are smaller. So further defining the concept of smaller, it just means closer to a base case, something that we can solve trivially. How much work do you need to sort an unsorted array of size 1? It's no work. I tell you that it's unsorted, but it's actually sorted. Because the concept of unsorted and sorted when your list is size 1 is the same idea. So you don't need further analysis. You don't need to break it down into subproblems. It's already solved. We then conquer the subproblems by solving them recursively. We're going to break this down into the smallest possible problems, solve them, and then take their solutions and combine them together into the solution to the larger problem. The solve them in merge sort is trivial. They will already be solved. But to create a sorted array of size 2 based on 2 sorted arrays that are of size 1, there's a little bit of work that we need to do. We need to figure out which of those 2 size 1 sorted arrays comes first when we combine them. So we'll combine the subproblem solutions to form a solution to the original problem. The absolute simplest recursive procedure that I like to disseminate is using the idea that you are in line for, think of the concert that you would most want to attend in the world. And you show up to the venue, but there's a massive line. It goes around the corner, down the block, etc. And by the time you park yourself in line, you have no idea how many people are in front of you, and you want to know how close you are to the front of the line for some reason. How long is it going to take me to get in once people are let in? Where am I going to try to fight for with regards to my positioning within this venue? So one way you might figure this out is you're going to tap the person on the shoulder in front of you and say, I have no idea how many people are in front of me. How many people are in front of you? And of course, the person who is right in front of you also has no idea how many people are in front of them. But we know that there's one more person in front of you than there is in front of them. That person is the one extra person that they're not going to account for. So once they turn around and are able to tell you there are 1,614 people in front of you, you would just add 1 to that and know how many people are in front of you. How do they answer how many people are in front of them? They tap the person in front of them and ask how many people are in front of you. They don't know, so they tap the shoulder of the person in front of them. And this works all the way down the line to the very beginning of the line. The first person in line knows they are the first person in line. There are 0 people in front of me. So they can turn around and relay that information. It's a basic version of this problem. It's trivially solved. I don't have to ask the person in front of me. There is nobody in front of me. There are 0 people in front of me. I can state that. If I turn around and tell that to the person behind me, there are 0 people in front of me. They can interpret that and say, well, if there are 0 people in front of you, that means there's 1 person in front of me. They've solved their version of the problem. They can turn around to the person behind them and say, there's 1 person in front of me. They'll interpret that as there are 2 people in front of them. This process just goes down the line until it gets back to you. You know now how many people there are in front of you. That is the recursive process. But do we agree that if we're looking at this problem, there is you and there is everyone in front of you? That breaks down into this person who says, I don't know, and a problem inside of that that looks exactly like this problem, which breaks down into that, and it just kind of zooms in like that, where we have the same problem inside of the same problem inside of the same problem. It looks a bit like Inception, where you're calling the same problem inside of the same problem inside of the same problem until there is a base problem that requires no analysis. That is your base case. So this is how I see recursion. It's the same thing with merge sort. We want to merge sort an array of size 16, we break it into 2 8s. We want to merge sort a size 8, we break it into 2 size 4. We want to merge sort a size 4, we break it into 2 times size 2. And it eventually breaks down into lists of size 1, which are already sorted. So take that same idea, and whenever we can apply that, we have a recursive solution. That said, if we're going to have that approach, we need some way of analyzing that approach. How do we come up with the runtime of merge sort? You were told the runtime of merge sort, and maybe you have a bit of an intuitive idea of how or why, but how can we do this mathematically? How can we determine the runtime of such an algorithm analytically? So it seems like, at least for now, we're going to dive into just talking about recurrences. And as needed, I might take a step back and talk some higher level recursion. Feel free to raise your hand and say, this makes absolutely no sense to me. I don't care if it makes sense to the rest of the class. It's good information for me to know that this is something that you are struggling with. And that can help me to ask the class, and I can determine in real time, is this worth taking that step back and going over something at a higher level for the class, or should I redirect you and those others who have questions about this to office hours? But I can't make that decision unless somebody knows or somebody tells me that they don't know what's going on. So that is very important information for me. All right. So we have some kind of recursive relationship in our code. We want to be able to figure out the complexity of this. So we are going to break it into the complexity of the base case and the complexity of the recursive case. We need to know how long does it take to answer that base case question. In the line example, that's the first person saying there's nobody in front of me. That is a constant time procedure because they don't need to ask anybody else. So the base case is always constant. But the base case may not be constant. The base case may be some other order, but it's important to know how complex is it to answer the base case question. You also need to know the complexity of the recursive case question. So base case, we will say T of whatever the base case size happens to be. This is usually 0 or 1. And we will relate that with some function that is independent of the size of the problem. For the first person who's standing in line, it doesn't matter how long the line is, to answer their position in line, it takes the same amount of time. So T of the base case usually always is independent of the size of the problem. The recursive case, on the other hand, will depend on the size of the problem. So we will get some function, usually based on n minus c or n divided by c, where c is some constant, where now we have a linearly smaller problem or proportionally smaller problem. So merge sort belongs to the n over c because we're going to divide the problem into twice as many problems of half the size. Whereas in our line example, that's more of an n minus c because every time we call the next iteration of that recursive function, the size of the line of that query is 1 less. When the person in front of me asks the person in front of them, the answer is going to be 1 less than it was. We're not dividing the problem in half, we're taking 1 from the size of the problem. So this just relates the complexity of the problem from my perspective to the complexity of the problem from the perspective of the person in front of me. Or in merge sort, the complexity of the problem with respect to the array that's now been halved in size. So how big are the subproblems? That will tell you what that looks like. And I think this makes a fairly natural place to stop for the day. We'll come back tomorrow and look at this in more detail. Feel free to swing by and ask any questions about what's going on in this class.
Oh, I'm wise.
Yes, it does.